Draw the shear and moment diagrams for the compound beam. To solve this, first of all, we need to recognize that this beam is made up of three separate sections or beams, and this section will not have any shear or moment. And then for the remaining sections, we have to solve them individually for their equations and for the external reaction forces before we can draw the diagram. And we need to find the equations just in case if the graph is going below or above the zero line of the shear or the moment diagram, which we just don't know yet. And I felt like it'll be a good practice if we figure those out as well, even if we don't need those. Alright, now to begin, let's draw the free body diagram of the section AB. For section AB, we can have a pin connection at A, so we can have both horizontal and vertical reaction force. Horizontal will be 0, and then the distributed load will be 10 kilonewton. And for B, there's a pin connection, and we don't know what the value for BY is. And now to find the value of AY, we just have to take the moment about the point A. So we're going to have, pardon me, at B to find the value of A. So we're going to have counterclockwise 10 kilonewton times 1 meter, and then clockwise AY 2 meters away, all equals to 0. Solving for AY, we have our solution as 5 kilonewton. And for BY, we just have to sum the forces in y direction, and we're going to have a solution as 5 kilonewton as well. Alright, now that we have all the reaction forces, now we can look for the equations. So to look for a shear equation, we need to find our load equation, which we know is going to be -5. And now if we take the integral of the load equation, we can have our shear equation. So our shear equation is simply -5x plus the constant. To find the value of constant, we know that our shear is going to be the value of AY, which is 5. And x at this time is going to be 0. Therefore, our C is +5. So it's going to be -5x plus constant C, which is 5. After that, for the moment equation, same idea. We're going to take integral of the shear equation. So we're going to have -5x squared divided by 2 plus 5x plus the constant. To find the value of the constant, we know our moment is going to be 0 when x is 0. Therefore, our constant is 0. And equation is going to be -5x squared divided by 2 plus 5x. So this is for region 1. BC, we're going to name it our region 2. We might have to subdivide it, or we'll check that later. For now, we're just going to assume it is one region. Okay, and so for our region 2, which is B to D, let's draw its free body diagram. So our free body diagram is going to be, our belly of the B is going to be opposite vector, whatever we had for AY, and BY we found it to be 5 kilonewton. And then we have our distributed load, which is 10 kilonewton. Then we have our CY, which is unknown. And then our dy is also unknown. Now to find the CY, we can say the moment about the point dy. Let's use a different color. So we're going to have counterclockwise 10 kilonewton, 1 meter away, clockwise CY, and then BY is counterclockwise 2 meters away, all equals to 0. Our CY is going to be 20 kilonewton, and by summing the forces in y direction, our value of dy is going to be -5 kilonewton. Now we can take the load equation and find our equation for shear and moment. So our shear and moment is going to be, our shear is going to be negative 5x plus the constant, and we know our shear is going to be negative 5x times 2 plus 5, which is going to be just positive 5. Because the negative 5x on this side is going to cancel out the negative 5 of the shear equation of the first one. So we're going to just left with the constant, which is positive. So it's going to be, our shear equation is same as the first region. So negative 5x plus 5. Similarly, we're going to take the moment equation, which is going to be just the integral of the shear. So we're going to have negative 5x squared divided by 2 plus 5x plus c. And to find the moment, we have to use our moment from region 1. So this equation and the current equation are same, therefore each of them will cancel each other out. So and our constant will be 0. Therefore our moment for region 2 is same as the other region as well. And just to verify, I'm going to just plug the value of 4, x equals to 4, and see if our moment equation is correct. If not, if we don't get to 0, we'll have to divide this region into 2 regions. So let's see. So if we plug x equals 4, we're going to have 16 divided by 2 plus 5 times 4 is 20. Our solution is negative 20, which in this case is not really correct. Therefore, what we have to do is divide our region 2 into 2 separate regions, because there is a change of forces in here as well. So what we're going to do is we're going to name B to C as region 2 and C to D as region 3. Alright, so our values for region 2 are going to be same, but the values for our region 2 might change. Let's see. So our equation for region 2, so let's see. So we're gonna have our load equation same as before, negative 5. Our shear equation is going to be same as well, at least the first part. Now let's see if our constant is same or not, because that's what determines everything here. So we know we're going to have push up from Cy, and Cy is 20 kilonewton. And then we have our value from the shear equation number 2, which is negative 5 times 3 plus 5. And then we have negative 5 times 3 plus c. So we know that this is negative 10. So negative 10 take away 20 is 10. And then we have negative 15 on this side. If we add by 15 on both sides, we're going to have our C as positive 25 for the shear. So the shear is going to be negative 5 plus our 25. And let's verify real quick. So our shear, let's see what our shear is when the value of x is 4. So we're going to have negative 5 times 4 plus 25. So we're going to be left with positive 5. And we know that our total is going to be 0 because we have negative 5 from the dy, the external reaction force, or in this case, reaction force from the member D marked here in the red. Alright, so this means we are on the right track. Now we can proceed to find our moment equation. So our moment equation is simply the integral of the shear. So we can have negative 5x squared divided by 2 plus 25x plus the constant. And for our moment, let's use our equation. So our equation for moment 2 is, I'm going to write it here so that I save some space. So we can have negative 5 times 3 squared divided by 2 plus 5 times 3. And on the other side, we have negative 5x squared divided by 2. But x in this case is going to become 3. And then we have plus 25 times 3 plus the constant. So this cancels out. We are left with 15 plus 25 times 3 is 75, which is negative on the other side, goes to the constant. So our C is 75 take away 15, which is 60. So our C is negative 60. So in our moment equation is going to be negative 5x squared divided by 2 plus 25x take away 60. And let's see if our moment equation is correct. It should be 0 at 4. So let's see if that becomes a reality. So we can have negative 5 times 4 squared. 4 squared is 16 divided by 2 plus 25 times 4 is 100. Take away 60. And yes, indeed, because this is 40, comes up to 0. So this means our equation is correct. Alright, so now that we have everything solved, we can draw our shear and moment diagrams. So let's start with our shear. So our shear is going to look something like this. So we're going to begin at 5 kilonewton. And then we're going to go downwards for 2 meters. So let's say our 2 meters is here. And we're going to go downwards for 10 kilonewtons. So that means our shear is going to be negative 5 kilonewton at 2, and it's going to be first order curve. At that point, we have this area, region 2, in here. So this region 2 is 5 kilonewton downwards. So this means from 5 for the next meter, we're going to go down another 5. I'm going to come to negative 10 kilonewton. And here at 3, we're going to get bump up from CY. CY is 20. So we're going to go up to positive 10 kilonewton. And once we are here, we're going to get pushed down again for 1 meter. So it'll be 4 meters. At 4 meters, we're going to go down 5 meters. So we're going to be at positive 5 kilonewton, and then dy is going to push us down another 5, and we're going to come down to 0. Because we are at 0, this means our diagram is correct. Now we can do the same for our moment. So our moment is we're going to begin at 0, and then we have this area, which is going to be at this intersect. We can either do that, find this intersection and then use the graphical method, or because we did all this hard work already, we found the equation, we could just plug the value, which is going to be 2 meters, into our moment equation number 1. So let's do that, because I don't want to do this long graphical method at this moment. So we're going to have 5 times 2 squared, which is 4, divided by 2. 5 times 4 is 20. 20 divided by 2 is negative 10. And then we have 5 times 2, which is 10. Interesting. Well, guys, looks like we do have to use the grinding method. Reason being because either we have to use every point in the x in order to determine the shape of the moment, or it's just going to give us the value of one particular point. In this case, how we did it, it just gives us the value of 0. Yes, we know that it's going to be 0 at 2 meters, but it doesn't really give us the overall shape. And overall shape, I already know that it's going to be a parabola upside down. And to do that, the best way is to just find this intersect of the shear, and we know that that is going to be our maximum of the moment equation. So let's do that, even though I know already, just looking at this, that it's going to be at 1. But this observation won't help us in more complex problems. So let's find our intersect. So for intersect, we need our, first of all, shear equation, which is negative 5x plus 5. And we want to find out where shear is 0. So we know that it's at 1. So now we know that the maximum point of the moment diagram is going to be at 1. And at 2, it's going to be 0. Okay. Alright, so we're going to draw our curves for both sides of the 1 meter mark. And we know it's going concaving downward, both of the curve lines. Okay, so that is done. Now for the next part. Next part, we have two distinct shapes here. So first one is negative 5 times 1. Second one is half times 1 times negative 5. So adding these together, we're going to have curve that is going to go downward because this area is negative till 0.75. And this curve is going to be concaving downwards. Oh, and one thing I forgot, the maximum. So for the maximum value of the region 1 is going to be just plugging in the value of 1 into our moment equation 1. So in this case, it's going to be, so if we plug it, it's going to be negative 2.5 plus 5, so 2.5. 2.5 is the maximum it goes in the positive direction. Alright, now for the other half, same idea, but on the positive side. And because all the dimensions and all the depths are the same, we know that this side is going to be positive 7.5. So at 4, we can have a concaving downward curve on the opposite side where we had the other curve. And with that, we have our final solution and we reach our